In this video we're going to look at factoring and solving polynomial equations. We're going to use a lot of what we already know about factoring from chapter 5 to help us in this section, but we're also going to need to know two special patterns for cubic polynomials. And these can be easy if you know the formula and you know how to apply it. If you don't remember the formula, then it's going to be very, very tricky and you're probably going to have a hard time factoring these. The two special patterns you need to know for cubic polynomials look like the following. There's a sum of two cubes which has the pattern a cubed plus b cubed. And that's all you have. You just have two terms. It's a binomial, but both terms are being cubed. In order to factor it, you have to ask yourself, all right, what's being cubed to get me a cubed? Well, that's just an a. And then you put a plus sign and you ask yourself, what's being cubed to get me b cubed? Well, that's just a b. So the first part of the factorization is just the binomial a plus b. To get the rest of this, what I like to do is I'll look at this part of the factorization where I have the a plus b, and then I just say, okay, it's going to be a squared minus the product of a times b, so it'll be minus ab, and then plus the second term there, b squared. That's the pattern. If you were to actually FOIL that out or multiply out that binomial and that trinomial, you will in fact get a cubed plus b cubed. Let's apply it in an example so you know what kind of it looks like in real life, so to speak. So if I have x cubed plus 8, that's a good example. It's a basic one. To get started, I always like to ask myself, what is being cubed to get me x cubed, or that first term cubed? Well, just an x. X to the third is x cubed. Then you have to ask yourself, okay, for the second term, what's being cubed to get me an 8? That would just be a 2, so it's going to have to be an x plus 2 here. Now this first binomial now matches the factorization a plus b. I can look to know what my a is and what my b is to kind of match it to the pattern. I know for this example, my a value is x and my b value is 2. Now, to get the rest of the factorization, remember, it was a squared minus ab plus b squared. So, in this example, a squared is really x squared. Then it's going to be minus a times b, which is really x times 2, in other words, 2x, plus the b value squared, which is 2 squared, or 4. If you were to multiply out that binomial and trinomial, you would get x cubed plus 8, but it's factored. So that's how we factor a sum of two cubes. The difference of two cubes is very, very similar. Instead of a cubed plus b cubed, the difference means we're just subtracting a cubed minus b cubed. It factors into the following. It'll be a minus b instead of a plus b, and then it's a squared plus ab plus b squared. Now, the example I'm going to use here will be similar. Let's do x cubed minus 8 in this example. Once again, to get started, I'm going to ask myself, what's being cubed to give me x cubed? An x. What's being cubed to get me an 8? That's a 2. But instead of a plus sign, it's got to be a minus now because it's a difference of two cubes. Now what do? Or what I do is I take this guy and I square it. That's going to be my a squared value. In this example, it's x squared. Then a plus sign. Then I got to multiply x times 2. That's going to be a 2x. Then I got to put a plus sign and do 2 squared, which is 4. If I were to multiply out x minus 2 times x squared plus 2x plus 4, I would get the difference of two cubes, x cubed minus 8. Now the way I remind myself of these patterns is, and if you notice, for both of these factoring patterns, what the polynomials or the factorization is the same. I have an a and a b, then an a squared, ab, and a b squared. It's just the sign changes are different. One thing that I remember is if I have a sum of two cubes, it's going to start with a plus sign, and then it alternates. So I do plus, minus, plus. And if I have a minus, I know I start with a minus and the rest are plus. That's the way I remembered it. I think Mr. Olson says something like, keep change positive. So what that means is if it's a sum of two cubes, you keep, for the first binomial, you keep the sign as positive. Then you change the sign for the next one, and then it's got to be positive at the end. So that also works for the difference of two cubes. You keep the sign the same as your difference, you change the sign for the second term, and it's got to be positive at the end. So you can think of the keep, change, and then positive as a way of remembering how the sign changes go. It's got to be the same sign, then change the sign, then positive to finish. I'm going to do two examples with you, and then at the end of the video you'll have a chance to practice a couple of your own. We're going to factor example 1. Now if you take a look at these, I have a 16u to the 5th and a 250u squared. That's not even a cubic polynomial. It's got a u to the 5th in there, and it doesn't fit the pattern. Do you remember the first rule we talked about when we factored before was always factor out the greatest common factor? So I definitely need to do that here. Now the GCF of 16 and 250, I don't know if a 4 goes in there. Let's see if, I think I can definitely take out a 2, and I know I can take out a u squared out of both terms. If I took out a 2u squared, I'm having a hard time with that 2, 16u to the 5th becomes 8u to the 3rd, and if I divide 250 by 2, I'd get a negative 125, and since I factored out the u squared, I would just have 8u cubed minus 125. That's good news because this is a difference of two cubes. And to factor it, I would have to copy down my GCF that I pulled out, and now I'm going to apply that special pattern. What's being cubed to give me 8u to the 3rd is a 2 and a u. 2 to the 3rd is 8, u to the 3rd is u to the 3rd. What's being cubed to get me 125 is 5. 5 to the 3rd is in fact 125. It's good to know your perfect cubes in this section. Now remember, I keep the sign to start. Now what I do is I square that first term. So 2u to the 2nd is really 4u squared. That's what needs to go here. Then I change the sign to a positive. Then I have to multiply the 2u and the 5. That's going to be a 10u. And then I remember I always end with a positive. So it'll be a 10u plus 5 squared is 25. Guys, that is factored. Here's the factorization. 2u squared times 2u minus 5 times 4u squared plus 10u plus 25. And we're all finished. Let's do one more example. 125 plus x cubed. It's okay, by the way, that the number starts and the x cubes at the end. It doesn't have to be in standard form for you to be able to factor it. There is no GCF, and actually this fits the special pattern right away. What's being cubed here is just a 5, as we saw in the last example. Since it's a plus, we're going to keep the sign as a plus, and what's being cubed in the second position is just an x. And then, to get it started, I'm going to square the 5 to get 25. Then remember, I change the sign. Instead of a plus, it's now minus. I multiply the 5 and the x together to get 5x. And then I always end with a positive, and then it's x squared. It doesn't say anything about having to write your polynomials in standard form, so it's okay, it's factored, and we can leave it as that. Let's go to the next slide. In this section, we're also going to have to factor by grouping, and we also factored by grouping when we did chapter 5, factoring quadratics, and so that's going to make this a lot easier. The key to knowing you're going to have to factor by grouping is you are going to have 4 terms in your problem. Do you see how in this example 3 I have 1, 2, 3, 4 terms? So always use when you see 4 terms. That's like the dead giveaway. Oops, I didn't want to go to the next slide. Darn it, I got to write it over again. So you're going to have to use when you have 4 terms. Use when you have 4 terms. Now, I have the 4 terms here, and you guys remember what to do. You pair up the first 2 and the last 2, and you take out the GCF of each pair. Out of the first pair, I can only pull out an x squared, and if I divide an x squared out of x cubed, I get an x. If I divide a negative 2x squared by x squared, I get a minus 2. Out of the second pair, the GCF is a 9. Now remember, if there was a negative there, we would pull out a negative 9. Usually that helps. So if I divide negative 9 into negative 9x, that'll leave a positive x. And 18 divided by negative 9 is minus 2. Remember how you want these binomials to match, and if they don't, you can't factor it by grouping. So I pull out and factor out the x minus 2 factor, and that leaves me with an x squared minus 9. Now in a lot of cases you'd probably be done, but we didn't factor it all the way down. If you remember, x squared minus 9 from chapter 5, that's a difference of 2 squares. I can actually go further. This is the same as x minus 2 if I just copy down that first one, right? But x squared minus 9 can be factored into x plus 3 times an x minus 3. And the typical question students have is it wrong if you left your answer here, right, as opposed to here? It's not as correct as it should be as my answer. It's not completely factored down. This is the better answer because it shows more factors. Is this one factored? Yes, but it's just not the best answer. So on a quiz or a test, I might take only 1 point off out of 3 or 4 or something like that. So always try to factor all the way down. Then the last thing I'm going to show you as far as factoring goes is things that are in quadratic form. I'm just going to show you a few examples, and I think it'll make sense from what we've seen in the past. If you look at example 4, I have two terms. I'm always going to try to pull out a GCF, and in this case, there is no GCF. And it's definitely not a difference of 2 cubes because 25 is not a perfect cube. But what I do notice is that it's a perfect square. Actually, this first term, isn't that a perfect square of 5 and an x squared? Like, meaning if I were to square that, I would get that, right? And isn't that also a perfect square of 6? Guys, this pattern is a difference of squares. The only thing that's a little bit different here is that it's not just like a 25x squared in the 36, it's 25x to the 4th. But who cares? X to the 4th is still a perfect square of x squared. So the difference of squares pattern, I'll just write it out again. If you had a squared minus b squared, remember that was just a plus b and then an a minus b. In this example, what's being squared in the first position was a 5x squared, and what was being squared in the second position was a 6. So it'd be 5x squared plus 6 and a 5x squared minus 6, and we're done. If you FOIL that out, you're going to get back to 25x to the 4th minus 36. Let's take a look at example 5. Now this one just looks plain old scary. It's got a's and b's. Let's see if there's a GCF we can pull out. I have an a squared and a but no a's in the last term. I have a b squared, b cubed, and b to the 4th. Each of these terms has at least a b squared. So let's start by factoring out a b squared. If I do, I'm going to be left with an a squared minus 8ab plus 16, oops, let me go back on that last stroke, plus 16b squared. Okay, now you might still think, man, this is pretty darn ugly. Yeah, it is a little ugly, but I still think we can factor this. That looks like a trinomial. It's just a quadratic trinomial. I think we can factor that. And it looks to me like it potentially could be a perfect square trinomial. Do you remember a perfect square trinomial? You square root the first term, square root of a squared is a. Square root the last term, square root of 16b squared would just be, what, 4b? And then since there's a minus here, I'd put a minus there. The way you have to double check that it fits the pattern, though, is you multiply these together and double it. So I'd have to do 2 times a times 4b. Isn't that 8ab? And hey, 8ab, 8ab, those match. So we're in business. Guys, this factors into just b squared times a minus 4b. I forgot something very important. We're supposed to square that binomial, right, once we factor the perfect square trinomial. So that fits the perfect square trinomial pattern we saw in chapter 5. Let's do one more example here. Oops, didn't want to do that. Didn't want to do that either. Here we go. This guy also looks like a trinomial that we saw in chapter 5. I'm just going to show you an example, and if I change this into x squared plus 4x minus 21, we would just be able to factor that into x and an x, and we'd find two numbers that multiply to make negative 21 and add to make positive 4, and I think that would be positive 7 and negative 3. Obviously, this is not the answer to the problem at hand. This is the factorization for this. The only thing that would change to make it match this particular problem is I'd have to make it, instead of x plus 7 and x minus 3, I can make it x squared plus 7 and x squared minus 3, because x squared times x squared makes x to the 4th. If I do x squared times negative 3, that's minus 3x squared. 7 times x squared is positive 7x squared. And then 7 times negative 3 would be negative 21. Doesn't that make x to the 4th plus 4x squared minus 21? That's what we started with. So guys, you can still factor in quadratic form polynomials that you can make fit the pattern. So just keep in mind, if you have an x to the 4th, you may need to change the first term. Instead of being x times x, you might have to make it x squared times x squared. So to just clean this up a little bit, our final answer here was x squared plus 7 and an x squared minus 3. Now, two more examples I'm going to show you. We're just going to solve polynomials by factoring. First thing you need to know is always set equal to 0 first. When we factored to solve, we had to do that in the other chapter. We got to do that here too. So I'm going to subtract 14x cubed from both sides to get 2x to the 5th minus 14x cubed plus 24x equal to 0. Now I look for a GCF. I know I can pull out a 2 and an x out of all these terms, leaving behind an x to the 4th minus 7x squared plus 12. And that's equal to 0. Now guys, I think this matches quadratic form. Instead of starting with an x and an x, though, I'm going to start with an x squared and an x squared, and I'm just going to see if I can find two terms that multiply, or two numbers rather, that multiply to make positive 12 and add to make negative 7. I think that's going to be negative 4 and a negative 3, right? Those will multiply to make positive 12, and they'll add to make negative 7. So this is the factorization. Ooh, by the way, check that guy out right there, that x squared minus 4. That's pretty nice. That can be factored even further because it's a difference of squares. That's really x plus 2 and an x minus 2. Now I can't do the same thing with that x cubed minus 3 because, oops, that's not an x cubed minus 3, it's an x squared minus 3. So x squared minus 3, that's not a difference of squares. Now, to solve, I just have to set each factor that contains an x equal to 0. So I have to set each of these equal to 0. I could set 2x equal to 0, or just x equal to 0. That'll give me 1 0 of x equals 0. If I set x plus 2 equal to 0, I get a solution of negative 2. If I set x minus 2 equal to 0, I get a 0 of 2. And if I set x squared minus 3 equal to 0, I would have to add 3 to both sides to get x squared equals 3. Then remember what we did? We had a square root to get x. So if I square root both sides, I'm going to get plus or minus the square root of 3. Don't forget the plus or minus sign. There's really two solutions there. So I have the following answers. I have 0, plus or minus 2, and then plus or minus the square root of 3. Really, if you count all those together, we have 5 solutions. So, pretty cool. Let's do one more. Part B. GCF looks like a 2 and a y, leaving behind a y to the 4th minus, 9? Now, y to the 4th minus 9 isn't very pretty. That's not a difference of cubes like the new factorization pattern we learned, but that is a difference of 2 squares. I can leave the 2y in front. Y to the 4th is really a y squared being squared, and then 9 is 3 being squared. So it'd be y squared plus 3, and then a y squared minus 3, just using the difference of squares pattern. I don't think I can go any further, so I just set 2y equal to 0, giving me y equals 0 as a solution. If I set y squared plus 3 equal to 0, I'd have to subtract 3, giving me y squared equals negative 3. And then when I square root, hopefully you remember what we got to do. Poke an eye out, plus or minus I radical 3. There's two imaginary solutions here. And if I set y squared minus 3 equal to 0 and add 3, I get y squared equals 3. If I square root, I get y equals plus or minus the square root of 3. Once again, I have 5 solutions. 2 of them are imaginary, but the other 3, the 0 and the plus or minus root 3, are the real solutions. Since we're already at 20 minutes, I'm going to stop the video here. What I'm going to ask that you do is I'm going to have you skip the word problem, and when you do your self-quiz, please do for me only these first 4 problems. Don't worry about doing number 5. We're going to do that in a later video. So good luck doing 1, 2, 3, and 4. Please look back at any examples that you've seen in the past that may help you, and we'll see how you do tomorrow in class. Thanks for watching.